Hi everyone, thank you for joining us for the Beyond Printf Real-Time UEFI Debugging webinar. We'll get started in just a few moments here. Thank you. Hi everyone, thank you again for joining us for Beyond Printf Real-Time UEFI Debugging as part of the UEFI 2021 Virtual Plugfest. I'd like to take a moment here to introduce our presenter, Alan Seguina. He's Vice President in Sales and Customer Service at Asset Intertech, Inc. And with that, I'll go ahead and pass it off to Alan.
Thank you, Megan, for the kind introduction. Appreciate it. Today, we're going to start off with a deep dive into some of the technology behind some of the trace logic that's inside Intel silicon. The more modern CPUs. Starting with the Intel Trace Hub. That is a event trace collection mechanism, and we'll speak specifically to the kind of sources, right? The logic within the chips that can steer trace data into the trace hub, and then the trace sinks, right? And once we take that compressed trace data, what do we do to it? Send it to system memory, right, out a port or whatnot. The flip side of the trace hub and event trace is instruction trace, code execution trace. So they're kind of two sides of the same coin. So we'll see how they work with each other and complement each other. It's a little bit of work setting up access to the Intel Trace Hub, right, as part of your debugging needs. So we'll delve into that, and then with the Trace Hub as an enabler, we'll set up at-speed Printf. One of the capabilities, one of many of the capabilities that's enabled by the Trace Hub. And then we'll have a demo where we show the Trace Hub, other trace sources in action, with an emphasis on the using the at-speed Printf. All right. So if you're doing low-level firmware debug, chances are you're aware of JTAG, right, as the primary access mechanism, right, and the enabling technology associated with looking at the silicon, right, the firmware, right, interactions with the board hardware, and so on. And the two main access mechanisms, the first one, of course, is the one that we're most familiar with, right, what we call open chassis debug, via the Intel XDP, the extended debug port. And that picture at the top right, if just to the right of the board, there's a little blue PCD and adapter board that has the XDP header on display down on the bottom right. And one of the first and maybe only generally publicly available and accessible boards that had provided access to the XDP header was the Minnow board. I spent many happy years playing with the Minnow board myself. Alas, it has been discontinued. So we've had to move to another one, and that's the board at the bottom right, which supports the Intel Direct Connect interface, the DCI. And this is closed chassis debug. You don't need that expensive hardware probe that you see there at the top right. You just plug into the target on a designated port, via a little specialty USB cable there with the yellow plug on it. That's closed chassis, of course. And just recently, you can purchase a board that supports DCI for closed chassis debug out of the gate. It's available over the counter, so to speak, and that's the Aeon Up Extreme i11. And I'll talk more about that board in a little bit. And next slide, please. There we go. So starting with Skylake, Intel really upped their game in terms of trace capabilities. Debug and trace on Intel platforms was pretty much the same for the best part of 20 years. And then Intel introduced both an instruction trace capability called Intel Processor Trace, which is code flow really, and then event trace, which is enabled by the Trace Hub. And if you're able to use both of those in conjunction with regular run control, setting breakpoints, halt, stop, go, those sort of things, you've really got unparalleled insight into the interactions between the silicon itself, the platform itself, the board hardware, the firmware itself, walking all the way up, if you want, into the operating system kernel and all, and looking for those complex interactions and system behaviors. So we'll delve into those trace capabilities with N0N specifically on an enhancement to the Printf capability. Intel Processor Trace is pretty much ubiquitous on Intel at this point. Atom, Core, Xeon, they all have it. It's a real-time, globally timestamped, highly compressed trace data. So you can run Intel Processor Trace and see the code flow, right? Both linearly and visually, as you see in the picture down on the bottom right. With really no significant impact. It's very compressed, very fast. You don't have to take any hit on execution speed. The restriction really of Intel Processor Trace is that the buffer has to be in system memory, right? So you have to wait until after system memory is initialized. You can use some of the other trace capabilities I'll mention later prior to that, but IPT kind of kicks in after MRC is complete. For event trace, Intel brought in the Intel Trace Hub, and it's really a funnel based on MIPI standards, STM, STPP2 technology. It's treated as a PCI device, so it's easy enough to configure. And what it does is, there's a bunch of logic blocks that know how to funnel their trace data in that standard format, into the Trace Hub. There's a trigger, right, a timestamp, and then it goes out the other side. And I'll show the different kind of trace sources in a moment. And you can send the trace data out to three primary destinations or mechanisms or sinks, right? One is the MTB, the Master Storage Controller Trace Buffer. You can get that trace data out of reset, which is really cool, but it's fairly small, just 8 kilobyte. System memory, you got lots of memory. You can, but you have to wait until after memory initialization. So that's kind of next. Best is via DCI, the Direct Connect interface. You can collect trace data out of an Intel platform directly out of reset. It streams out the USB port, that specialty USB port, that specialty USB cable, and you collect the trace data in the debug host, not the target, but the debug host system memory. So you can collect gobs and gobs of trace data directly out of reset, with DCI easily enough. I did a webinar with the UEFI forum back in February on architectural event trace, or AET. And I think, as far as I know, that's probably the most in-depth or public disclosure on some of the functionality within AET. So at the risk of being a little immodest, it's well worth watching. But AET collects trace data for the listed event types and subtypes that are in this table. And AET is extremely powerful. And I highlight about 2/3 of the way down in the table the code breakpoint and the data breakpoint event types, which can be caught. And what Intel does with AET is it micro-architecturally changes the behavior of the breakpoint, not to actually stop the target, but it runs past, but collects the breakpoint as an event. And you can also collect the LBR stack, the last branch record stack, a few hundreds worth of instruction trace, right, at each event as well. And you'll see that as part of the demo. Really, really powerful stuff for debugging purposes. And the star of the show is the software firmware trace. And one of the things you can do with this actually is create an at-speed version of Printf. Requires you to roll up your sleeves a little bit, but and update. Presuming you have source, right, and you can build an image with this facility inside of it. But what it essentially enables you to do is run the Printf not out the serial port and not by executing those thousands, tens of thousands of instructions associated with the serial port right, the Printf itself, but rather steer that data through to the trace hub, right? And then don't send the full format string out the trace hub, but rather a pointer to the format string and let the remote debug host do the heavy lifting. So this just speeds up the boot flow. You essentially get the performance, the speed of a release build, but it's a debug build, and you're able to see your Printf data in immediate, meaningful code context, with instruction trace and correlating AET and so on. So this is really the way to go if you've got one of those really sort of intermittent, really difficult to triage kind of bugs that could be race conditions, concurrent programming issues, and whatnot. And it's correlated, right? All the data is timestamped, but then it's correlated with Intel processor trace, architectural event trace, and run control. So we'll get into that. Just a little cheat sheet for the syncs, a little bit of a further explanation on DCI, which is available publicly now, and is the subject of this demo actually. Right, there's two flavors. The older version actually is the DBC3, and DBC2, which we used in the demo and which is available on that Tiger Lake board, is gives you some capabilities that are not present with DBC3 in terms of debugging through power state transitions, for example. All right, so two steps really in terms of getting the at-speed Printf working and enabling. First off, you have to enable the Intel Trace Hub has got to be enabled, and that's typically configured, within the BIOS to turn it on and off. Not always though, right? The board's BIOS needs to support that, and what you want to do is use the debugger to access the Trace Hub early. And in fact, on client platforms, you can turn it on right out of reset, because about a third of the way, as the platform boots, about a third of the way, the PCI, as a PCI device, it gets hidden, and you can't thereby configure and access it later. But if you get to it early enough, you can turn it on and debug trace to your heart's content. Now for at-speed Printf, right, you need to hook the regular debug type statements, the debug type printfs, and replace those with calls, a little bit of modified code as part of the asset system trace library. So you've got the debug macro, right, that you want to hook, RC printf or MRC printf, and the assert. And I'll show in a minute, kind of a little bit, peel the onion back a little bit more detail in terms of how that's done. But once you make those changes, right, rebuild your image, you would use, you can use Printf as you normally would, and Printf or at-speed Printf, the whole build, or at-speed Printf, just the modules of interest. All right, so for implementations, just a little bit of a deeper dive into the code, and I presume you can download these slides, of course. via your control panel. And there's a very detailed user guide, right, and sample code available, open source sample code available that you can retrieve via our website. But first off, you make a change, you add in support for the system trace library in made package.dsc, add in the required header files, C files, and now you can use the library via either one of those top two mechanisms, right? You can modify and change the INF file from base debug lib serial port to base debug lib system trace. That essentially replaces that and goes through the trace hub. Or if you want to be a little bit more selective, perhaps, and use that speed printf on specific modules, right? You can use a compiler flag, build flags, right, as illustrated in number 2 there, and put a little bit of conditional code in the places where you want it to be. And down at the bottom, going from left to right via the green arrow, you can see just a little bit what the code looks like. You can download this thing and crawl through it, of course, yourselves. But we basically hook an invocation of serial port write, which does the full printf and goes out the serial port and all that good stuff, and replace that with system trace write and do the equivalent and go through the trace hub and use the remote host to do the heavy lifting associated with printing out the format string. This is another little cheat sheet, is just for DCI, right? Hopefully this is helpful for people that end up diving into this with some pleasure and having some fun, right? If you're debugging prior to memory being initialized or prior to MRC completion, actually, what you want to do on the instruction trace side is use last branch record, right? That's that MSR-based trace capability. Only gives you a few hundred worth of instructions, but that's what's available prior to MRC completion. And then for the event trace, though, you got it all, right? Trace hubs available auto reset, and you can trace events such as the architectural event trace, with or without the LBR traceback, and you can do the management engine, the ME trace, message trace, the @speed printf, and so on. And after MRC completion, you can use full Intel processor trace and collect tons of instruction trace data, because you're going into system memory at that point. And event trace is the same for the entire boot flow. All right, without much further ado, I'm going to jump into the end of the demo, and what you're going to see is the JTAG debugger, the host-based debugger, communicating with an isolate client target over that specialty USB cable. So no hardware probe involved here, and the cable's anywhere from $10, $11, $20, I think, different lengths available, and you can pull that down. You can order those from Intel Design and Tools or Data Pro. You can get that over the web. Now for the demo, what I did is, like I have in the past, I've recorded the demo, no audio, just the video, because usually I do get tripped up during these sort of public events, by Murphy's Law, if I try to do too many things at once. And I sped up certain parts of the video, so I'll just talk over it. I'll speak to it as we go through, so we can speed things up, slow things down. Right? If I decide to pause, I can do that. So let me. I'm going to share my screen and switch to my video player here. All right, and let's make that a little larger. And hit play and talk to it all at the same time. So what you're seeing right now is the debugger connected to the isolate target. You can see from the viewpoint window that the target is actually in a running state. We haven't halted it yet, and we're switching over to the serial console, right? The putty, you can see the shell as we're sitting in the shell. So I'm gonna reset the target. And so I'm going to halt the target, excuse me, and I immediately stops and refreshes the code window, and we can see we're in just a kind of arbitrary point in code, right? That's the instruction pointer, the yellow bar, and an arrow, right? So we're just kind of sitting there. Now it gets interesting. We're going to reset the target, and I've got, in this case, a reset turns into a power cycle on this particular target, and I've set some breakpoints at the reset vector. So we halt there at the hardware breakpoint at the familiar 7F0 no op that you see. And of course, we're in a stop state at this point. So we can do the basic run control actions like single step and so on and so forth, right? So we hit that step into button, and you can see the instruction pointer move, right? We're in early code. Oh, excuse me about that. Didn't turn off my notifications. Anyway, so that's where we are. We're early in the code, and we're at the reset vector. Now we're going to, on Intel client platforms, we can actually enable the trace hub at this early part of the code. So and we do that via a macro, right, which simply configures the trace hub, and it's north peak, right, synonym for trace hub, enable. We force it on. A couple of parameters associated with turning on timestamps and doing a hard configuration of the trace hub, and away it goes. Now we have we've discovered the trace hub, and now we can steer some trace data to it. And there's you have to configure it. There's a few tricks to configure it that's associated with a macro, right? We want to set the logging level essentially to override or complement whatever you might have in terms of error level and priority level, within your code, right? Make sure that we're getting the correct level of verbosity, as it were, especially out of the printf statements. All right, so given that is set up, now what we have to do is actually set up configure the trace sources and the trace sinks, via the facilities that are provided, within the debugger. So we scroll up to the trace window there, and let's make it a little bit bigger so we can see what's going on. And we do hit the configure button. So here's all the trace that's supported on Intel platforms. LBR, we don't really need that right now. BTS is branch trace and store, an older version. We don't use that anymore anyway. Trace hub here. So we just have to check a few boxes. First off, we have to define, via XML, the masters and channels, the sources essentially, that we're going to trace. And there's a bunch of them. And I happen to know, I'm taking a shortcut here, but I happen to know that hex 18 and hex 75 respectively stand for AET and the at-speed printf. So I'll just say okay, and I'll get back to that, how I know that, in a moment. Going to steer the sync, not to system memory, not to MTB, but rather going out that DCI cable. And here's where I do my little bit of cheating, right? You have to, of course, use make the master channel definitions known to the debugger by using the appropriate ports file. And I go into my installation directory within the debugger. I click on the targets folder. It's an isolate client folder. Now here's how I configure the trace hub and make sure that the right data is going to the right place, and just say okay. And I'll go back in again just to show right now that the actual trace sources are disclosed, right? So you can see we've got access to the ME messages if we want them. AET, we did check that one off, so that's good to go. Scrolling down a little bit, right? These are all part of the XML, the port definitions. And hex 75 was at the hosted printf, the at-speed printf. So now all that printf stuff is going to go in and out of the trace hub instead. So anyway, that's all you really need to do. And then you just go ahead and click on OK. And we want to set up AET because that was one of the trace sources that we picked, right? So we got to fill in a little bit of detail here. We got the option of what, which threads you want to trace and which events you want to capture. And for this demo, I'm going to show the read MSR and the write MSR. And I'm going to activate the LBR stack so I can see the code flow associated with the collection of these events. So now trace is all set up and all configured. I set a breakpoint at core install configuration table. It's a function in Dixie, right, that initializes the instrumental and initializing some of the system tables. And I'm just going to run the target now and collect all of that trace data. Now, I've used technology to speed that up a little bit so we don't have to wait for the whole platform to boot. But here we go. We see that we've hit the breakpoint and we've collected a bunch of event trace data. In this case, the AET data, right from the reset vector, the very first read MSR, and can go back in time, as it were, and see every single read and write of MSR registers, right, done by the platform, all the way from reset to halting, within Dixie. And you've got the disassembly, of course. We've got no source code to the port at this point, but you can see the disassembly associated with that. Scrolling back in time, oops, I went a little too far. Scrolling back and find the that MSR read was done, 416.666 nanoseconds, right, after the halt, right, where I was previously halted. And you can see the MSR address used and the data that was read. Scrolling back, there's the next MSR read, 10.132 milliseconds after reset. Read from MSR platform info, C-hex-CE. And let's remember that data, because you're going to see that again, right? On the data that was read was F8810E00. Because that's obvious. That was actually the object of a Printf that we'll see in a bit. Scrolling back further in time, you can see we have some source code, right? We're up in an area that we have code. I've interleaved the assembly language, with the source code statements as well, just because I enjoy reading assembler as well. And 18.834 seconds after boot, right? You see this, another MSR read, for hex FE and the associated data there. So yeah, you can obviously collect this data, save it, and let's look at it in the context of whatever else is going on the target. I'm going to change the display here a little bit. Right now we can see, we'll be able to see the @speed printf, the hosted printf. I want to change the display a little bit because we don't really, in this instance, want to see so much the AET data. Already saw that stuff. Or you want to look at the hosted printf data. So there it is. So this is normally stuff you'd be looking at on the serial console. Now you can see it in the context of the debugger. And that's directly from where we were halted near the reset vector. And for the modules that I've enabled, that's here. And you can see that one there, the 28 seconds into milliseconds into the boot flow at that state number. You can use either one to correlate. And you can see that there's a printf that prints out the MSR platform info on this target, F8810E00. So you see, and it's an easy way to correlate, what you might be getting out of your printfs, as well as what actually happening on the target in terms of an event and an actual code flow, right? You can trace that back, obviously, in assembler or source code, whatever you happen to have available, right, at that point. So very, very powerful, obviously, and happening at speed. To mix it up a little bit, that was all event trace. Now I'm going to switch over to code execution trace and use Intel processor trace. So we can see all this, how all this fits together. I'm still only going to trace on thread 0, and I want to have the same timestamp, the cycle accurate timestamp. And I've already set up my base address around 4 gig on this platform to store the instruction trace data. Now, I'm going to take off the breakpoint associated with core install configuration table because it gets called a bunch of times to do a bunch of work. I'm just going to hit the go button now and switch over to the PuTTY window and just boot the platform and collect a bunch of Intel processor trace data here. And I'll just run it to the UEFI shell here for grins. Not much is happening at the UEFI shell. That's interesting from a code perspective, but let's look at that anyway. Halted at the shell, and my Intel processor trace window refreshes, with the code flow associated with where we were, which was halted at the first invocation of core install configuration table, all the way back to sitting at the UEFI shell. I could change. There's 100 different ways to configure the display. I kind of like to see the source lines repeated and the assembly language lines under explicitly called out under each. But you can certainly change that, and you can collect as much or as little Intel processor trace prior to the prior halt as you want, and this obviously, I mean, you can see how the code is flowing in a linear flat fashion. If you actually want to see a little bit more visually, you can do it with a call tree or a call chart. And here's the call tree, and this is really just a explicit nested calls. You can see this really good at the UEFI shell, right? Nested calls of the individual functions that are being invoked time and time again, the timestamps with them, and the inclusive and excluding time, right? Excluding the time spent in the subfunctions associated with each one of those functions. So export that, do some analysis. You want to see it visually, you invoke the call chart. And that's from the point of the last halt at the right and going back 133 microseconds. That happens to be how much trace data we collected here. Move the cursor or marker to look at individual places within the code and expand or contract or scale, right? So you can examine things a little bit more deeply, right? Especially when you're looking at the lower level functions that might be only invoked for a slice, as it were. So that's really it. That's Intel processor trace, event trace, with AAT and the hosted Printf, and all running at speed, and just a lot of utilities, that a lot of facilities, debug and trace facilities that Intel has provided in its most recent silicon to make our firmware development and debug a little bit easier. All right, so I'm going to get out of that, and if I may go stop sharing and switch back to the slides. All right, so just finishing up. What are the our view within ACID is we really want to have UEFI development and debug being not the purview of the select few, but really everybody should jump in and look at the learning and development, personal and professional development opportunities associated with this fascinating and very interesting field. And the links in here are some worthwhile lookups. Intel and Eclipsium did a fantastic presentation at the Open Source Firmware Conference a couple of years ago, before the pandemic, on debugging Intel firmware on an Apollo Lake board with DCI and USB 3.0. Right, and things have moved along since, right? I mean, now, anybody and everybody, can acquire a USB 2.0, a DBC2 DCI solution on that Tiger Lake board. So, really expanding and opening up possibilities, for individual research, learning and whatnot. I did mention my debug webinar with the UEFI forum in February on AET, more of a deeper dive. I just kind of touched the surface today, and the asset blog. Stay tuned for always. We're always continually writing about our experiences in firmware development and debug. So feel free to subscribe to that. And if you want to take the next step and access the at-scale Printf support files, they're available on our website in the SourcePoint Academy. Ignore that @speed at Printf at the end. Just go to that SourcePoint Academy link, and you'll find the support files and documentations associated with that. And I think with that, that's all I have for now. Over to you, Megan, with any questions.
Thanks, Alan. The first question we have here is, what are the functional differences between using DCI and accessing the XDP with an external hardware box?
Okay. Covered that just a touch. There's several differences. One, of course, is that you don't have to buy the box, or you don't have to have the box. So there's a hardware cost that's avoided by going with DCI. And the key thing is that the streaming trace capability, right? If that's something that you need as part of your development and debug, and you want to capture that event trace out of reset, for example, right? You can capture a limited amount with the MTB, but and if you don't want to wait until after the memory is initialized, right, DCI is the way to go.
Next question here. Do you know if AMD is working on anything similar to the Trace Hub?
Oh, that is a good question. I do not know the answer to that question. We'd have to ask AMD about that one. It would be great if they had it, but I'm not really sure.
Next question here. What about debugging of commercial boards? Is DCI applicable?
Yes, actually, fairly recently. Yes, it is. Normally, of course, the laptops, desktops, server that you have, you purchase, those have DCI disabled. But Aon has two boards out the door. One is that Apollo Lake board, right? Which unfortunately, run control doesn't really work that well on it. So it's not really a suitable platform, though it does have a source code published on firmware.intel.com. Just recently, on one of the earlier slides, I pointed out the Aon Up Extreme i11. And I think there's a few flavors of it, and Core i3, Core i5, Core i7. That's a Tiger Lake board, actually, and it has DCI operational, right? I think it just rolled off the out of the factory floors, like maybe 5 or 6 weeks ago, as a matter of fact. But you can do DCI debug on that Tiger Lake board. That's the preferred platform.
Could you elaborate a bit more on using AET with instruction trace?
Certainly. Two flavors of it. One is check the box with the LBR box next to the event in the AET configuration window. So what that will do is as the platform runs and the trace hub is capturing the event data associated with the AET sources, like read or write MSRs or IO or exceptions or whatnot, right? You can capture that LBR stack and have it all display in one window. Once you hit the halt, right? All the events are displayed, and the prior LBR backtrace, which runs 200 or 300 instructions, give or take, right, is going to show up in that same window. So you can see the event, each of the individual events, right, and then the instructions that the code that led up to it. Instruction trace comes in the other flavor being the Intel processor trace. And that's the one I showed at the very end of the demo, where you're actually capturing all, as much as you want, instruction trace data, and you correlate those with the cycles and with the global timestamp.
What about straight out of the reset vector processor trace streaming over NPK? In other words, what's the average timing impact of a printf over NPK?
It's nominal. I don't think we've ever measured it, but it's got to be a 100-fold improvement, roughly, in terms of performance versus going out the serial port, via the printf execution statements, versus using the trace hub, the compressed trace data, and the pointer to the printf string.
Is the JTAG DCI transport protocol something that is available if we want to connect our own debugger to it?
No, to my knowledge, that is those are proprietary.
Great. And so what is, and I may be saying this incorrectly, SVEN, and how does it relate to ASPF?
Right. Yes. SVEN. Okay, I'm gonna try the acronym. System Visibility Event Nexus, I believe. It is it's a facility that's in, I think, some of the Intel builds, and what that is, it's kind of a little bit slower version, as it were, of at speed printf, the ASPF. What SVEN does essentially is it does avoid the serial port, right? It does steer the printf data through the trace hub, as opposed to through that super slow to the serial console. But it's slower, about a factor of 7 to 10 times slower than at speed printf, based on the mechanism used to print the debug format string.
All right, great. And so that is actually the last question that we have time for today. But that being said, we are moving over to WebEx now for a live Q&A opportunity. So I'm putting the information is displayed on your screen, and it's also displayed on announcement as well. So please move over there with us if you have any additional questions for Alan, or if you'd like to talk to him directly about any of the content that he reviewed today. Thank you all again for attending the UEFI 2021 Virtual Plug Fest. These slides will be available on the UEFI forum website, and this video recording will be available on Bright Talks and YouTube. So thank you all so much.
Thanks very much, all.